Hello world, it's Angelat, and we're back with another dots on a map tutorial. This time I want to show how we can add interactivity to our dots, especially when we have a lot more of them. So I've added a data set where there's about 6,000 cities. They're all, with populations greater than 50,000 people, and we're plotting them on the map. They're all over the world. And for this, for the sake of example, we're just highlighting the ones near the mouse cursor. Whatever your application may be, you might want to display a little bit of info. You might want this radius to be much smaller so that you're hovering, you're getting the closest point to the mouse. Maybe you're rendering in canvas, something that would be nice to do with this many points. 6,000 DOM elements is quite a bit of work for the browser, and that's what's making the zooming and panning a little slow. But what's not slow is selecting this subset of the 6,000 cities and highlighting them when we move our mouse. So let's talk about how to do that. I mentioned this Quadtree thing. It's a D3 algorithm, or sorry, it's an algorithm implemented in D3, and it's typically used to do things like select a small subset of a big scatter plot. Maybe if you click near something, it gives you the nearest points. But it's almost always using XY coordinates in all the examples I've seen, at least. That means the actual pixels in your block. Whereas on a map, we have XY coordinates. That's how we're plotting our circles. You may remember from the previous videos, we turn lat long into XY. But we also know that every time you zoom and pan, you have to recalculate the XY coordinates for our circles. And if we used a Quadtree like the other examples on the XY, we'd have to recalculate our Quadtree every time we zoomed and pan. And so that's something we want to avoid by using latitude longitude coordinates for our Quadtree. So let me show you some code on how I modified our previous example to support this type of interaction. And we're also going to go over why we see this as an ellipse, especially as we get farther north, and as we go south it becomes more of a circle, and what we can do about that. So I have some code that will offer some trade-offs there, and we'll talk a little bit about map projections and distortion. So let's just get started though. The first thing we notice is that we have our radius variable here, and we're saying basically we want to select all cities that are within 1.5 degrees of our mouse cursor. And we also have this pixel radius, which will come into play once we decide that we want it to always be a circle, and how how we can accomplish that. This code here is just setting up our map from our previous tutorials. Go ahead and check out one of the earlier videos to see how that works and how we set up an SVG layer that moves with the map. Here we're creating an ellipse, which is an SVG element. It's basically a circle that can have a different X radius from Y radius. We'll see our projection functions, which again came from our previous tutorial, and we're still loading our CSV of dots. In this case it's a little bit bigger list of cities, and we're still rendering our dots in SVG the same way as we were before. So we pass in our data from our CSV and create circles for each city, and then we have our render function, which updates the position, the XY position of our circles every time the user zooms and pans, which is controlled here again from our previous tutorials. So here's where the new stuff starts. So a Quadtree is like a lot of other D3 things you might have used, like a d3.svg.line or other things, right? You're basically creating a function that you're going to use later, and you're setting up some things about it. So in this case, we're telling it, the Quadtree depends on X and Y coordinates because it's going to actually create this tree of quadrants. It's going to make all these boxes that it uses internally. You can just think of as ways to sort of avoid having to search through all your points. And we're telling it that we want it to use the longitude for X and the latitude for Y. directly. So we're not using pixels, we're using the actual longitude, latitude. And by doing this, we are kind of getting into the situation where the further north you go, the more elliptical things get, because at least in the Mercator projection, the further north you go, the more spread out the latitude is relative to the longitude. But near the equator, they're closer to a grid. So we'll deal with that more in a second. And when we move the mouse, we basically want to move our little guiding circle, which is mostly for the purpose of this demonstration, as well as calculate the nearest cities. So the first thing we do is we just get the center point, the projected center point of our mouse position, right? So Mapbox gives you this event which has a longitude, latitude, and we can project it just like we project our cities. And then we set the cx and cy of our ellipse to that. So that's just like a circle, right? The x and y coordinates of the center. And what we need to figure out is the radius x and y for this ellipse so that we can draw it. And we do that by just doing a little bit of math trickery, right? Like we know what the radius is in degrees. So we say, like, let's say we're just considering the x radius. We take the center point where our mouse is, and we just add the radius to that in degrees. And then we project this point, because it's just moved over here. We already have this point projected, and then we subtract the two here, so we get the distance between them in pixels. And the absolute value, right, is just so that it will never be negative, but that distance will always be some positive number. And then we do the same thing in the y direction. We add the radius in, to our latitude of our mouse coordinate, and then we project that point and subtract the two, and then we get this distance. And even though the radius in degrees is the same in latitude, longitude, there is a difference in the pixel distances, right? And that's why we get the ellipse. And so then we can draw this here. So then that's just to draw this ellipse. Because our Quadtree works in latitude, longitude coordinates, it's already, even we give it a single radius, and it's going to do kind of a circle around the longitude, latitude of our mouse coordinate and find all the points that are within that radius in degrees. And therefore, that's why it's selecting this ellipse, because it's doing it in the lat long coordinate space rather than in the pixel space. So I'm going to go over quickly how this nearest function works. It's something we've defined below. It's I've essentially forked it from some of these other examples and modified it to use latitude, longitude rather than x and y. And we're going to talk a little bit about this visit thing. Because the Quadtree, it has, the thing you might use more commonly is this find function, which given a point will give you the closest point, like just one closest point. But in this case, we wanted to get everything sort of around the mouse. And for that, we need to visit the points in our Quadtree and ask for the nearest ones, based on our radius. And kind of one of the slightly weird things about the way this nearest function works and the way that the Quadtree visit stuff is that we're passing in this hits array, which starts out empty, but this nearest function is going to fill that hits array with all the data points that are close to the mouse, right, based on our criteria. So let's take a look at this function. Oh wait, before we do, once we get everything in the hits array that we want, we select all the circles, we turn off the highlight class on all of them, regardless if they have it or not. Then we filter down our selection to any circle whose datum is inside our hits array. And for those, we set the highlight class true, and all the highlight class does is set the fill color to pink. So how does our nearest function work? And this is a bit complicated, a little bit mathy. I'll try my best to explain it. One key takeaway though is that you can find this in some of these other examples, and the main difference is just that instead of and lat, it's x and y, or it's 0 and 1 for array indices, and the other key point here is like our points long and lat. And so I didn't really change much of the logic. It's just the accessors to the data. And the thing to keep in mind is that our node is essentially our mouse coordinate, right? So that's why it has long and lat. That comes from Mapbox. That's just the way that those are set up. And then this quad.point is referring to an actual data point. So like one of the cities, and this is like the Quadtree's internal way of keeping track of stuff. It puts a point, for whatever data point, and that will have a long and lat because that's what our data looks like. And you remember we gave our accessor functions further up that say, oh, use long and lat. So let's just talk through a little bit about how this works, because we created a function that returns a function, and that returns a Boolean. So what's going on here, right? Basically, we're giving the Quadtree a function that it can run on each quad. And to understand a little bit better, a Quadtree splits up the screen like into quarters. So here you can see that when I click here, it's in this this top left quarter. There's more off the screen. And then when I click here, then we know that it's actually in the top half of this quarter, it's in this top corner. So as the Quadtree goes, it first says, okay, which quarter of the screen am I in, right? I'm in the top left. So that means I don't have to look through any of these points or anything outside of this top left corner. Then it goes to the next level. Okay, out in this corner, let me split it into 4 pieces. I'm in the top right corner of this level, so I don't need to look through any of these, right? And so on and so forth. And you can see that there's a ton of stuff that it doesn't need to loop through. There's a ton of points that it doesn't need to even worry about when it's saying, oh, is this point close to my given mouse coordinate or whatever it is, right? So that's kind of a really quick overview of the Quadtree. And that's why this is returning a Boolean, because we're basically saying, is the node we clicked on within this quadrant? And if it's not, then we can just stop looking at that quadrant and we can ignore all the points that are within that quadrant. And then sort of the meat of things are right here, where we're calculating the distance. This is sort of this is the distance function between our mouse coordinate and the point and a given point that we're looking at. And we have our radius that was passed in, and so we say, is the distance less than the radius? If it is, we're pushing our point onto our hits array. So I don't blame you if that was too quick and a little complex. I encourage you to play with these other examples. Go ahead and console log what's going on in here. I'm actually going to try to make a Quadtree, like an in-depth Quadtree tutorial, but for now, suffice it to say, we've just adapted this nearest neighbors function from another XY example to work in lat long, and when we get our hits, we can highlight stuff. Okay, so we've done that, but let's say we don't really like this whole ellipse thing. And there's a couple options. One is we could sort of account for the projection's distortion and use a different radius for the lat and a different radius for the long. Another way is you might say, all right, and a whole nother sort of like UX principle would be, instead of it being by degree, so that, a nice thing about using the radius in degrees is that no matter what your zoom level is, you're always going to get the same density of points when you hover around, right? So if I zoom way out and I'm hovering over here, I'm only selecting these 3 points. But if I zoom in and I stay in the same spot, I'm still selecting those same 3 points, right? And so it's kind of nice, because a lot of cases when you zoom out a lot, you don't necessarily want to select hundreds of points as the user goes. But you may want to still think about stuff in pixels if that's not a concern. And let's show how that works. So here I've set a radius of 45 pixels, and I can actually just uncomment some code. I'm going to comment this Quadtree, and I'm going to uncomment this code. And what we're going to do is we're going to have a circular, let's see here, and then I need to change our little ellipse here so it's not using this stuff. So now we have a circular selection, and you can see no matter where I am, it's not elliptical, north, south, whatever. It's always 45 pixels. So what happens is if I zoom in, now my 45 pixels will select less things, and if I zoom out, those same 45 pixels will select more things. And in some cases that's desired semantics, right? You know, like you're always kind of just highlighting some area around the mouse, because as you saw before, when you zoomed out, that circle got pretty small, and if you zoomed out a whole lot, that wouldn't be very useful, right? So this gets into the territory of what's best for your application, right? So it's good to have options, and let's just take a look at how we accomplish this option. And so here we're doing a similar thing as before when we were trying to calculate the radiuses, but we're doing it backwards. We're essentially saying, okay, given our x coordinate plus the radius in pixels, turn that unprojected into the longitude and latitude point for the our longitude's radius, let's say, and get the distance in degrees. And then we'll do the same thing for the latitude, and since we're doing it, you know, y plus the radius in pixels, what happens is we'll get a different radius in degrees for the same radius in pixels, right? So before we got a different radius in pixels when we started from degrees, and so now we can pass in those two different radii to our nearest to function, which is slightly modified, and I'll show you the modification, so that it will, instead of finding the points in a circle, it's actually going to try to detect things in an ellipse in lat long, which will end up being a circle in our projected space. So I mean, I know this is getting confusing when we're thinking back and forth, but if you want to do this, I invite you to study this code a little bit more. But basically, our nearest to function is very similar to our nearest one function, where we're now passing in two radii, and we're still doing the quad part, but this time instead of being squares, it's going to end up being some kind of rectangle, right? And we're still saying, you can return early if the quad we're in does not fit inside our rectangle, thereby discarding all those points. And then we've made a small change to the way we determine whether you're inside the ellipse. Namely, you have to, the x distance between our mouse coordinate and the given node needs to be less than the radius in the x direction, and the distance between the latitude of our mouse coordinate and our data point needs to be less than the latitude radius. And if those two things are true, you'll be inside the ellipse, and therefore we'll push our hit on there. So that is how we're using Quadtrees inside, with geo coordinates, and we are avoiding having to recalculate the Quadtree every time the mouse moves by just calculating it once on latitude and longitude. You may want to scale the radius, or the radii used here, the pixel radius, depending on zoom level, but I leave that sort of as an exercise for you to try on your own, basically using the map scale and calculating stuff in here. There's all kinds of different ways this can be taken. I'd love to see examples if anyone applies this. Tweet it at me or shoot me an email. So I hope this was useful. I enjoy this technique and hope to catch you at the next tutorial. Thanks. Bye.